Hypothalamus artificial intelligence. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents its solutions for Pandemic Management Decision Support System. Part 5. Epidemic State Estimation using Kalman Filter Modeling. The presentation consists of 5 videos, and their supporting documents, which summarize all the applied research work carried out by HI, to contribute its knowledge in highly complex mathematical modeling, to the optimized management of pandemics such as COVID-19. These are: Pandemic Management using Advanced Artificial Intelligence, Epidemic Simulation Model, General Epidemic Optimization Model, Epidemic Economic Impact Model, and Kalman Filter Estimation Model of the Epidemic State. The models corresponding to Part 4 and 5 are designed, but have not been implemented. Users of these mathematical models can be grouped into information technology companies, government, universities and research centers, and private enterprises and gremial organizations. The result of the research and mathematical models carried out by Hypothalamus Artificial Intelligence, it is considered a public good, because it is of benefit to all humanity. Therefore, HI is willing to offer them at no cost to nonprofit organizations, mainly in developing countries. HI is also interested in being part of research groups working on pandemic management. Conference prepared and edited by Jesus Velasquez Bermudez. His resume can be found on LinkedIn. The decision-making during the pandemic process aims to make the best decision for society, which is not easy, nor intuitive. The problem is further complicated, when decisions must be made with real constraints on available resources. The traditional goal of pandemic management focuses on modifying the natural behavior of the pandemic, solid curve, through sanitary controls, in order to reduce the peak of infected people, striped curve, and thus save lives by reducing the deficit of hospital resource capacity. However, it should be noted that the two curves have the same integral, and in theory when time tends to infinity, the amount of the infected population will be equal. If hospital resources are sufficient, there is no reason to delay the peak, and as the pandemic spreads, the negative socio-economic impact will be greater. The traditional tool is to use simple epidemic simulation models, trying to predict the future of the pandemic, before different control measures, and thus select, based on perception, which is the best decision. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus is obtained. In the case of the epidemic, HI has conceptualized the epidemic management hypothalamus based on 4 models: epidemic model, logistic model, economic model, and control and surveillance model. This video is related with the control and surveillance model. COVID-19 surveillance. This webinar presents the integration of machine learning, ML, and state estimation to implement machine learning algorithms to understand the behavior of a pandemic system using advanced algorithms based on the fundamental concepts that support the so-called Kalman filter, KF. The multiple state Kalman filter, MSKF, and the dual Kalman filter, DKF, are integrated to model the state of the pandemic, that is, the distribution of the population in epidemic states, and the parameters of the differential equation epidemic model. MSKF is a methodology that allows to combine the process of determination of possible Markovian states where can be a system, with response functions identified by Kalman filter for each of the possible states of the system. The selection of the probability of the Markov state in which the system is located is determined based on a Bayesian inference model. DKF is a methodology that allows, simultaneously, estimate the state variables of the process being analyzed, and the parameters of the dynamic equations that govern the process. The learning process associate to integrated MSKF and DKF, thereinafter DMSKF, can be termed as a deep learning process, since it assumes the process of identification of parameters as part of the dynamics of the system, without preset a response function as stationary and certain. The dynamics of the DMSKF allows to re-estimate the system response function, considering the information contained in the data more recent. It may include the dynamic selection of the structure of the differential equations that explain the epidemic process. The working paper. Epidemic state and parameter estimation using dynamic machine learning based on a dual multi-state Kalman filter. Presents in detail the mathematical formulation of the concepts of this short webinar. Uncertainty dynamic systems. Under the state estimation approach, an uncertain dynamical system, whatever it may be, can be conceptualized as consisting of two systems or components. Physical model. The system dynamics can be represented based on a set of differential equations, or differences, based on mathematical laws. Typically, these equations are referred to as the system model. The state in which the system is located is referenced by the vector of state variables, xt. The state equation, which defines the gradient of state variables, has a known structural function that depends on a set of parameters, beta t. The ut vector is related to control variables, which humans can manipulate to control the system. Observation model. On the other hand, a measurement system, which observes the dynamical system by the variable zt, is related to the state variables by a vector function ht. The vector function ht can directly measure state variables, or measure transformations of these variables. Additionally, this observation system can include multiple measurement systems, from different sources. Together, the two components make up what in artificial intelligence is called a hybrid system, which combines information from the physical model with measurements from the observation system. To build it, two types of knowledge are usually required. That of the field expert, in this case an aerospace engineer, or similar, and that of a data scientist. The traditional is to use models based on mathematical models of the system, or models based on the data. The construction of the state equations requires complex mathematical knowledge, and therefore they are not commonly used. However, without an observing system, these isolated physical models contribute little to the online estimation and forecasting of the system's trajectory. Data-driven models are much easier to build, but they ignore scientific knowledge of the mathematical laws that govern the behavior of the system. By integrating the two models, state estimation becomes a robust hybrid method, capable of producing the best possible results, in terms of forecasting the state of the system. The concepts of state estimation are applicable to multiple types of systems. A few are mentioned below. Vehicles guidance, hydroclimatic variables, satellite imagery processing, economic systems, mass consumer products forecast. The diagram presents the evolution of a dynamical system. At instant t-1, the value of the state variables is known, xt-1, using the equations of system dynamics, the value of the state variables in t, xt, can be estimated. Iteratively, xt plus 1 can be used to calculate xt plus 2, and so on. To control the system, control variables must be included. The state variables are observed through the measurement system, which produces the zt variables that are an xt transformation. To optimize the process, it is desirable to use the dynamic programming approach, which includes an objective function, usually the cost of running the system. Since optimization must be carried out in a planning horizon, which usually covers more than one period, all periods must be chained together, and an optimization problem must be formulated. The objective function is the sum of costs in all periods. Given the uncertain nature of the system, it is necessary to incorporate state estimation, to obtain accurate information of the state of the system, in probabilistic terms, and perform a stochastic dynamic optimization process. Kalman was best known for his co-invention and development of the Kalman filter, a mathematical linear algorithm that since its origins has been widely used in signal processing, control and guidance systems, navigation and control. Subsequently, the Kalman filter has been used in almost all sectors of the economy. And it can be considered the best hybrid methodology of quantitative predictive artificial intelligence. The approach for the state estimation, SE, is supported on a conception of the stochastic processes, where the random variables are clearly differentiated of the measures, being understood that the modeler has data of the measurement system, that may be different from real values of the random variables. Therefore, all available observations are considered as random variables, having their measure information, but which, by reason of the randomness of the measuring system, are subject of precision errors, therefore, assume them as deterministic induces errors. Moreover, there might be more than one measure for a random variable, obtained by different sources. Two types of noise, or errors, are considered in state estimation modeling. Epsilon t, errors due to the modeling of the system, reflecting the uncertainty of knowledge of functions, equations or parameters, that determine the behavior of the system that is modeling, and theta t, measurement errors that come from the precision with which the random variables associated with the system are measured. The conventional statistical models only consider one type of error, μt, which integrates modeling errors and measurement errors, whereas the state estimation modeling differs clearly the two types of errors. This may be the principal advantage of state estimation modeling over the traditional statistical modeling. Typically, the system modeling error, epsilon t, is totally ignored, since the method is concentrated on the error in observed data. The historical data is assumed deterministic. The conventional statistical models only consider one type of error, μt, which integrates modeling errors and measurement errors, whereas the state estimation modeling differs clearly the two types of errors. This may be the principal advantage of state estimation modeling over the traditional statistical modeling. Typically, the system modeling error, epsilon t, is totally ignored, since the method is concentrated on the error in observed data. The historical data is assumed deterministic. The pandemic as a dynamic system under uncertainty. The traditional way of mathematically modeling pandemics is based on systems of differential equations that explain the process of virus diffusion. The equations showed are of the SEIMR model. The susceptible infectious recovered model, SEIMR, introduced by Kermack and McKendrick in 1927, is the basic epidemic model. It describes the pandemic based on three states for a person: susceptible, infectious, and recovered, based on a system of three interrelated differential equations. This state transition diagram of the SEIMR model enriches the original description, including three additional states: NP, new population arriving, ND, natural dead, and ED, epidemic dead. In the case of the SEIMR model, the state variables that define the trajectory of the pandemic are the amount of people, susceptible, infectious, and recovered. The parameters of the model are infectious rate, beta, and recovery rate, gamma. State variables and parameters correspond to random variables, since it is not known with certainty what their true value is. On the other hand, there is the pandemic information system, which is decisive to know the behavior of the pandemic, and to estimate the parameters that define the differential equations. The image shows the timeline of COVID-19 events in Hubei, China. The gray curve presents the actual status of the pandemic, and the yellow curve was reported by Hubei city authorities. It is easy to visualize the large discrepancy that exists between the two curves. In general, there is a delay in detecting what is happening. The gray curve may become known in the future, but it is not known at the time decisions are made. Therefore, decisions must be supported by the yellow curve, which is known to be incorrect. This situation is not the best, and it must be improved. This can be achieved using methodologies based on state estimation, including control variables, such as confinements, mitigations, etc. The model has an appropriate structure to use state estimation modeling and dynamic programming. Then, the sources of pandemic uncertainty dynamic process are about state and control variables. What is the true value of variables that represent the state of the system? This is the number of people in each epidemiological state. What is the true value of the variables that represent the control system? What is the impact of control measures? For example, which is the true percentage of a quarantine measure? About mathematical model. What is the true model that represents the epidemic process? SEIMR. What is the true value of the parameters associated with the equations of the mathematical model? Are they static? Or are they dynamic? How is the function that defines the dynamic variation? About observation system. What is the accuracy of the measurement system? Is there more than one measurement system? All these uncertainties are the real case. Then, COVID-19 surveillance is a state estimation problem. From the point of view of managing a pandemic, the mathematical problems to be known. To define the structure of the models of differential equations that govern the behavior of the pandemic. To estimate the parameters that define a specific model within the infinity of possible models to describe the dynamic process. To know the true state of the pandemic, which is defined by the number of people, or by the fraction of the population, which is in each epidemiological state. The importance of an appropriate estimation of the parameters of mathematical models and the state of the pandemic is determinant of the decision-making process to control the pandemic. At least two problems must be faced. In new pandemics, such as COVID-19, the structure of mathematical equations can be unknown and is therefore part of the problem to be solved. The system of measuring pandemic states can be very poor, mainly in the early pandemic and in countries with little capacity to widely measure the population and determine their epidemic status. State estimation and Kalman filtering. The interested professional can see detailed information in another complementary video. Rudy Emil Kalman was a Hungarian-born American electrical engineer, mathematician, and inventor. Rudolf Kalman was born in Budapest in 1930. After emigrating to the United States in 1943, he earned his bachelor's degree in 1953 and his master's degree in 1954, both from the Massachusetts Institute of Technology. Kalman completed his doctorate in 1957 at Columbia University in New York City. Kalman was most noted for his co-invention and development of the Kalman filter, a mathematical algorithm that is widely used in signal processing, control systems, and guidance, navigation and control. For this work, U.S. President Barack Obama awarded Kalman the National Medal of Science on October 7, 2009. Kalman filter theory. The KF process has as its starting point the dynamic equation of state variables, which has as its input the a posteriori prediction in t-1, and the control variables in t. The result is the a priori estimate of the state variables for period t. The result is the a priori estimate of the state variables for period t. On the other hand, the system that is being observed, through the measurement system, produces the actual measurements. The comparison between the estimate a priori of zt and the real value of zt, produces an error, or innovation, that is used to make corrections in the state variables. This is done by means of the so-called gain matrix, M, which is a central part of the KF. The result is the a posterior estimation of xt, which will be the starting point to carry out the process in the next period, t+1. We ignore the past as much as the future. Of the present we generally ignore where we are. The stochastic processes where the random variables are clearly differentiated of them measures allow the modeler to improve knowledge of the past based on the evidence of the present. It can only be realized by a combination of forward and backward processes. If t1 is the period for which you want to obtain the best estimator of the state variables, given the information received up to t. The relationship between t1 and t defines several types of process. Smoothing, t1 less than t, it involves predicting a posteriori the state variable in the past t1, before t. Filtering, t1 equals t, it involves the correction, filter, of the prediction of the state variables in t, while reaches the information. Forecasting, t1 greater than t, it involves the prediction of the state variables for periods t1 after the present t. The last two functions are the most used, however. The prediction of the past makes perfect sense when we recognize that in the past, we only had estimates of the state variable, because we never know its real value, which can be improved by processing the information coming later to t1. Traditional statistical models assume that history is a deterministic fact, that is known by the observed values, and that this values cannot be changed. State estimation models assume that we ignore the past almost as much as the future, and for the present we have a rough idea of where we are. As we acquire information, uncertainty in all directions must decrease. Smoothing is fundamental in the process of estimating the epidemic state, because due to the type of process, it is necessary to reconstruct, in the best possible way, the history of the epidemic, since an inappropriate interpretation will give rise to bad decisions, since they are made based on measures that do not reflect the reality that is happening. That case happened in Hubei, in the early days of the pandemic. Then, in the case of the pandemic, predicting the past could be much more important than predicting the future. Variations and extensions of Kalman filter. Considering that KF is oriented to linear dynamic systems, an effective algorithm for identifying an industrial or a natural process may be considered as a combination of the following methodologies: Kalman filter, extended Kalman filter, ensemble Kalman filter, dual Kalman filter, Bayesian model combination, and multiple Markovian state Kalman filter. For the epidemic estimation model, the algorithms dual Kalman filter, DKF, Bayesian model combination, BCM, and multiple Markovian state Kalman filter, MSKF, are considered adequate. Multi-methodologies Kalman filter. The advantages of the approach based on the integration of multiples methodologies of state estimation versus the classical methods are presented below. One of the limitations in the modeling of uncertainty dynamic systems is that related to the hypothesis that the response function is known a priori, and structural changes of the system cannot be easily modeled. The response function of a system reflects the way its internal structure works. Structural changes cause changes in the response function and cannot always be expected. Many of the changes that occur in the behavior of a system are consequences of unexpected events. Before these eventualities, schemes based on multiple system states, or similar, to determine the moments in which structural changes occur, differentiating them from pure stochastic effects. From the point of view of control, the state estimation allows the online analysis of the phenomena that are occurring, while conventional methods are aimed at ex post analysis, to describe phenomena already past. Dual state estimation of state variables and model parameters. When the true value of the parameters of dynamic, the equation of state variables, is unknown, DKF uses two filters that act in parallel, one on state variables, and one on parameters of a statistical model, or of the physical model. Based on this approach, there are multiple theoretical variations. Here will be considered the one presented by Labar et al. The diagram summarizes the process. The diagram shows the connectivity of the standard Kalman filter. The DKF includes an additional filter on the parameters, in order to simultaneously correct state variables and parameters of the dynamic equations. Bayesian combination of models. There are multiple models to simulate the pandemic process. The state transition diagram presents the SEIMR model, the best known and simplest of all. The SEIMR model is an evolution of the SEIMR model. The state transition diagram presents the SEIMR model. The SEIMR model is an evolution of SEIMR model. The state transition diagram presents the SEIMR model. This implies that there is more than one model to describe a pandemic, and the true model is not necessarily known. The question is, which is the real, or the best model? BCM is an extension of the Kalman filter theory, oriented to compare simultaneously several models of a system. The theoretical development that follows specify a model M based on the set of parameters and estimators of model I. Using the Bayes theorem, BCM calculates the a posteriori probability that a model I is the true model. The prediction can be obtained through a combination of models, each multiplied by the probability that it is the true model. In this way, it is possible for the model to change over time, selecting the one that best fits dynamically, since the probabilities of the models change in each period t. Multi-Markovian system state Kalman filter. Multi-Markovian system state Kalman filter, MSKF, Velasquez, 1978, corresponds to the extension of the theory of the Kalman filter to model systems whose dynamic representation depends on the state, or regime, in which the system is. Examples of a system state status can be a person, good temper, temper, or quiet. In a watershed, dry, wet, or in transition. In a client, happy, indifferent, or unhappy. Epidemic state estimation, stable, growing, decreasing. There are plenty of examples that can be cited. In all of them, the response of the system can respond to stimuli in the environment, in accordance with the state in which the system is located, which in many cases is not fully identified, because it is a random variable. Therefore, the concept of system states may be associated with a semi-Markov process, time-dependent transition matrices, where the probability of transition from one state to another, at any period t, it is not stationary and can be changed over time, depending on what is happening in the system. In this case, the regime, system state, in which the system is located, should be considered as a state variable which must be estimated online. The system state may be associate to a state of a Markov chain. Modeling implies that the a priori probability that the system is in a state I is known, and the probability, a posteriori, that the system has made a transition from state I to state j, must be estimated based on the information obtained during period t. From this information, the a posteriori probability that the system is in a system state I is known. T diagram shows the system states for river basin. T diagram shows the system states for an epidemic model. MSKF allows to assume dynamic structures for the variation of the parameters, which leads to more flexible models, that the obtained making use of limited tools, that offer classical statistics-based methods. It must be also understood, that state estimation process corresponds to a Bayesian inference process, where the estimators are recalculated when new information arrived. From this point of view, the identification of behavior a system is not limited to evaluate parameters that summarize the average behavior of the system as a result of integrating its variability on a last period, and from there to consider the calibrated model as static model. The real problem is the determination of the estimators of the parameters, representing best dynamics of the system in accordance with the observed data, for the instant of current time t. It implies concentrating the effort in the assessment of the changes that are occurring, than is possible to determine in real-time structural system changes, that are reflected in changes in the values of the parameters, which in classical models only occurs after these changes have occurred. The hypothalamus of a pandemic decision support system. Pandemic management optimization process implies research in the following areas: epidemic theory, smart sampling, identification of epidemic model parameters and the epidemic state, and mathematical programming optimization models oriented to control and management of the pandemic process. The diagram presents a possible connectivity between the state estimation models and the pandemic management optimization models. The diagram presents the flow of the pandemic management optimization process. The above flowchart should be adjusted to include the state estimation models, as a preliminary step to the parameter models of the optimization models. Hypothalamus Artificial Intelligence invites to join to the LinkedIn group. Mathematical modeling for coronavirus pandemic. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.